Hello and welcome back to another exciting day of statics. Today we're going to talk about internal forces. Up to this point, we've really talked about external forces and how they're applied and finding reaction forces, but internal forces are something that we've kind of touched on a little bit. We've talked about compression and tension in members, but we're going to kind of dive into that a little bit more detail in this chapter. And this video, really, we are going to concentrate our talk on what those forces are in what we call slender members in both 2 dimensions and 3 dimensions. So what are internal forces? They are forces and moments that develop inside the structural member itself due to external forces applied to that member. In statics, again, we focus primarily on determining the internal forces in slender structural members. A slender structural member is really one that has a cross-sectional dimensions that are much smaller compared to its overall length. The disaster that we see here is the Cypress Viaduct in Oakland, California, and the failure of a support column occurred during a 1989 earthquake, which led to the collapse of the upper deck onto the expressway of the lower deck. The column failed really because it could not support the internal forces that were needed for that structure. So here are a few common examples of things that we might think of as slender members. We can look at the bike with the tubing and the bike itself as being a structural or slender member. Human femurs. On this pier we see many of these columns here. This long beam between the piers are also slender members. The information that we learn from this chapter also carries on and goes further into the mechanics of materials on the failures of these beams and deflections of beams. There are many members that are not slender members. Here's an example of one. This is a one-piece crankcase, and it's a casting for a small engine. It is a very complex design, and determining the forces internal to a structure like this really takes a lot more analysis than what we will be doing. A lot of it is computer analysis using like finite element analysis. Okay, so I have a member here which we will call a slender member. It may go on very long on us. And what we want to do is, again, look at what those internal forces are due to these externally applied forces or moments or distributed loads, which we just talked about. And what we want to do is take a cut in this member and look at what types of forces we have. The 3 main types of forces that we have are our axial load, and that is what we've kind of dealt with before. This tells us if we're in tension or compression. The sign convention that we will use, we will always draw these pulling away from the member itself. We also have something called shear force. Shear force acts along the surface of our cut. And you'll see between these 2 halves, of course, they have to again be equal and opposite. The convention, it says no sign convention here, but this is the convention that we will be using when we have a beam. When we have other structures that aren't beams, it's more open-ended that way. And last, we have a moment, our bending moment, and we may have bending in the beam when they're long, and we have a moment. So we have these 3 internal forces that we will see when we cut a beam, and they are our axial force, our shear force, and our bending force. And in mechanics of materials, we look at this a little bit more. Again, we've kind of touched on this with our tension and compression. This axial force N causes this shape to either grow in length in tension, or it could shrink if it was in compression. So those are the 2 things that axial loading will do for our beam. Shear essentially kind of makes the beam want to skew. You can think of taking a book, and if you take your textbook, put it on the table, and hold the bottom of the book stationary, and then push real hard on the top cover of the book, you will see that it will want to slide, and you'll get this sliding action between the pages. That is a shear force that's developed between those layers of that book. And that is due to this force that is, again, parallel to the cut surface. Last, in 2 dimensions, we have a moment. And this moment does this bending action of deformation, right? And this way that it's drawn right here is really considered to be a positive moment. I think of it as a happy face, right? That's the bending moment if we do it in that direction. Negative is if I'm bending downward like this when I cut it, and it will have a negative shape and it's kind of a sad face. In 3 dimensions, we have the same ones that we talked about in 2 dimensions, but we add some other components to it. We still have our normal axial load that we have on here. We have our shear in the VY direction, so they're equal and opposite, but we're adding with shear also something in the Z direction. Okay, so we add an additional force for shear, and then we add in a couple other things for our moments. We had the Z, which was a bending moment that we talked about earlier. There's also a bending moment around this other axis that we can have, the Y-axis. And then last is the bending moment along the axis of the shaft or beam itself. This is a twisting or torque type action. So how do we solve for these internal forces? There are a couple methods of doing this. The first one is this equilibrium approach for finding internal forces. And what we do in this approach is we identify the cross-section that we're interested in, and what we do then is take a cut through that section of where we're interested. We draw our free body diagrams, and then introduce or draw in our appropriate internal forces or unknowns. And again, that's the ones we just talked about, our normal force, our shear force, and then our moment. Then we apply, of course, our equations of equilibrium to solve for unknowns. And then if desired, maybe there's other cuts and other locations we want to know these values for, we would take additional cuts. What we're looking for typically is for failure where we may see the highest of these values. That's kind of typically what we're looking for when we do this type of analysis. I will run through one quick example in this lecture. I will post other examples, especially one in 3D, which I think you should also look at. This example talks about a C-clamp is used to press 2 pieces of wood together while they are being glued. If the clamping force is 200 newtons, determine the internal forces acting at the cross-section through point A. So we are interested in this section here, and that's where we will take our cut. You see that point A isn't really centered on it. It's through this centroid, and that's something you would learn later on about in mechanics of materials, that we look at the forces through that centroid. Okay, so the first thing we're going to want to do is draw our free body diagrams, and I will do that right now. So here we see our components. We're compressing this wood again with 200 newtons to allow it to glue. We have this threaded rod on top, which is clamping down on it with this 200 Newton force. This section is in compression, we can see. Then if we look at the C-clamp part, we have this section here, which has 200 newtons on either side. Okay, so I'm interested in having a cut through this through point A and see what we get from there. So if I cut that and move that down below, we can finish up our free body diagram at this location. What we have at this location then again is our internal forces. Our normal force is always perpendicular to our cut. That is our N. I'm going to call it N sub A because it's at a specific location. We have a shear force. In an object like this, there is no right direction or wrong direction. That's V sub A. Shear is always a V letter, and then I'm going to put a positive moment. M sub A is our bending moment. Okay, last I just added in the dimensions for our free body diagram, and now we can use our equations of equilibrium to start solving for this particular free body diagram. Easily enough, we see that if we sum forces in the x direction, all we have in that direction is a positive VA, which tells us VA, our shear, is equal to 0. If I sum forces in the y direction, set that equal to 0. In the y direction, I have a positive NA and a minus 200 newtons. We find that NA is actually in tension of 200 newtons. And then last, we will look at the moment, and with some moments at A, set that equal to 0. We have a NA, which is 200 newtons times a distance of 50 millimeters, and it is a positive moment. And then I also have a positive moment the way I drew it, MA. We can solve for MA, then equals a minus 10 Newton meters, or 10 Newton meters clockwise. I converted the millimeters. This really comes out to 10,000 Newton millimeters. I converted it to Newton meters. So there we have our solution for this clamp.